Good evening. Welcome to the summer workshop on plasma physics, and I am Swarnish Chandra. So today we are on our ninth lecture, and we will be starting with our first part, that is the plasma waves. So in plasma physics, waves or plasma waves are an interconnected set of particles and fields, of course, which propagate in a periodically repeating fashion. A plasma is therefore a quasi-neutral electrically conductive fluid. Quasi-neutral, we know this term. In the simplest case, it's composed of a electron and a single species of positive ions. But it may also contain multiple ion species, including negative ions as well as neutral particles, also positrons, dust particles, and many more. Due to its electrical conductivity, a plasma couples to the electric field and the magnetic field. This complex of particles and fields support a wide range of or a wide variety of wave phenomena. So in plasma waves, the electromagnetic fields in a plasma are assumed to have two parts, one static equilibrium part and the another one is oscillating or the perturbing part. So waves in plasma can be classified as electromagnetic or electrostatic according to whether or not there is an oscillating magnetic field. If there is a constant magnetic field, it's electrostatic. But if it is a fluctuating one, it's a electromagnetic. So applying the Faraday's law of induction to the plane waves, we find that this expression k cross E is equal to omega b, implying that an electrostatic wave must be purely longitudinal. An electromagnetic wave, in contrast, must have a transverse component, but may also be partially longitudinal. Now this is to be discussed in a later part. In plasma waves, the classification is carried out by the oscillating species. In most plasmas of interest that we will be studying, the electron temperature is comparable to or larger than the ion temperature. This is because the electrons are more mobile and compared to the ions, and they have more kinetic energy, and therefore the temperature is also high. This fact, coupled with the much smaller mass of the electron, implies that the electrons move much faster than the ions. An electron mode depends on the mass of the electrons, but the ions may be assumed to be infinitely massive, that is stationary ions. An ion mode depends on the ion mass, but the electrons are assumed to be massless and to redistribute themselves instantaneously according to the Boltzmann distribution, that is exponential minus E by kT. Only rarely that in the lower hybrid oscillations, about this mode we'll talk later, there will be a mode dependent on both the electron and the ion mass. So the plasma waves, there are various modes. It is also classified according to whether they propagate in an unmagnetized plasma or parallel and or perpendicular or even obliquely, making an angle to the stationary magnetic field. Here the stationary magnetic field determines the direction or the classification. Finally, for perpendicular electromagnetic electron waves, the perturbed electric field can be parallel or perpendicular to the stationary magnetic field. So here we give a list or table is taken from the internet. So you can see that based on the electromagnetic character, there are electrostatic and electromagnetic. Now there are ions and electrons. If electrons are the oscillating species, in case of electrostatic mode, there are two modes: the plasma oscillation or the Langmuir waves and the upper hybrid oscillations. On the other hand, if the ions are the oscillating species, then there are ionogastric wave, electrostatic ion cyclotron wave, and the lower hybrid oscillations. In case of electromagnetic, there are a variety of it. You see, O wave, X wave, light wave, Whistler mode, and if the ions are the oscillating part, we have the Alban wave and the magnetosonic wave. Well, Alban wave, let me say, it is named after Hans Alban. He was a Nobel laureate and a great physicist. Now in part 2 or part B, we will study about the plasma oscillations. Now, plasma oscillations, also known as the Langmuir wave, are rapid oscillations of the electron density in conducting media, such as plasmas or metals in the ultraviolet region. The oscillations can be described as an instability to the dielectric function. Now, here this dielectric function d is related to the particle density and in a different way with the wave number and all those things. We'll study about it later. So the quasi-particles resulting from the quantization of these oscillations is the plasma. What is a quasi-particle? We have dealt with quasi-particle before. For instance, the phonon. Well, what is a quasi-particle? In physics, quasi-particles are collective excitations which are closely related and occur when a microscopically complicated system such as a solid behaves as if it is contained differently with weakly interacting particles in free space. For example, an electron, while traveling through a semiconductor, its motion is distributed by a complex way by its interaction with all of the other electrons and the ions or the nuclei. However, it approximately behaves like an electron with a effective mass. Now, the electron with a different mass or the effective mass is known as the electron quasi-particle. We call it a effective mass. Electron with effective mass is also an electron quasi-particle. In other example, the aggregate motion of electrons in the valence band in a semiconductor or hole. So the hole is also a quasi-particle. Is the same as that of the material, instead contain positively charged quasi-particles called holes. Other quasi-particles are the plasmas, phonons. Now, these quasi-particles and the term collective excitations, there are both terms used. Now, quasi-particles are those particles which follow the Fermi-Dirac distributions, and the collective excitations are the its counterpart that follow the Bose-Einstein statistics. Okay, so let's come to our initial discussion. So Langmuir waves were discovered by Langmuir and Tonks, Levi Tonks, and I've given the original paper. So you can check it. So what is the mechanism of plasma oscillations? Consider an electrically neutral plasma in equilibrium consisting of a gas of positively charged ions and negative electrons. If one displaces by a tiny amount an electron or a group of electrons with respect to the ions, that is the electron cloud, the Coulomb force pulls the electrons back, acting as a restoring force. Here the Coulomb interaction is the restoring force. In this discussion, we need to know two terms, the cold and the warm electrons. Well, if the thermal motions of the electrons is ignored, it is possible to show that the charge density oscillates at the plasma frequency. This we have given this expression in both units, SI and CGS, because many times we will have a set of equations given in the CGS form as well. So we know that plasma frequency is equal to square root of electron density times electron charge square E square divided by mass times epsilon naught. Now here I have put m star is the effective mass. You can put me if you want. Now this is generally a good approximation as the electrons are very lighter compared to the ions. So in case of electron positron plasma that is found in space, because space has got a huge variety of particles, so in astrophysics we have encountered such electron positron plasmas. So the expressions get a bit modified. Since the frequency is independent of the wavelength, these oscillations have an infinite phase velocity and zero group velocity. You see from this term that if it is independent of wavelength, then wavelength 1 by wavelength is k. So if k remains in the denominator, so it will be 0, and therefore the term is infinite. Now, what about the warm electrons? When the effects of the electron thermal speed given by V thermal is equal to kT by me are taken into account, the electron pressure acts as a restoring force, as well as the electric field and the oscillations propagate with frequency and wave number related by the longitudinal Langmuir wave. Now you see, this is the longitudinal Langmuir waves expression. It's also known as the Baum-Gross dispersion relation. If the spatial scale is large compared to the Debye length, because in plasma, one of the plasma parameters is the Debye length. If the spatial scale is compared large to the Debye length, the oscillations are weakly modified by the stress or pressure term. But at small scale, this pressure term is very much important and it dominates, and the waves become dispersionless, and its speed is √3 times the thermal velocity. For such a wave, however, the electron thermal speed is comparable to the phase speed of the wave. So the plasma wave can accelerate electrons that are moving with speed nearly equal to the phase velocity of the wave, that is in phase. The process often leads to a form of collisionless damping. Okay, energy dies out and it's known as Landau damping. You just check about Landau damping, or we'll just put it in another lecture. Consequently, the larger k portion of the dispersion relation is difficult to observe. What happens with large k values, that is small wavelength? No one knows, or no one knows. I would say that it's not of that much importance, and we won't study that in our discussion and workshop. So let me give you some example of the few wave modes in plasma. We have said electron acoustic wave, where there are two kind of electrons, warm and cold. The warm electrons provide the inertia, they provide the restoring force, and the cold electrons provide the inertia. The electron plasma waves are high frequency plasma waves. Ion acoustics are low frequency wave modes where ions execute the oscillations. Here dust acoustic wave, here dust particles. What are dust particles? Dust particles are, suppose, a small dust particle which accumulates electrons on its surface and becomes charged. Okay, then it behaves as a grain, and the plasma modes are generated. Alveolar waves and the magnetosonic waves. Then many more are there. Okay, so thank you for your patience. So in the next lecture, we'll be studying about some of the wave modes in details. Till then, goodbye.